Okay, hi everyone. This is Dan Barry from the NOAA Climate Program Office, and thanks for joining for today's webinar. We're very excited about this webinar. It's part one of a two-part webinar. The second part will be held tomorrow. And, we all kind of felt that this hurricane season's had an alarming impact on lives, property, and the environment, and wanted to communicate what we're doing in response to that in this portion of the scientific community. So that sense of alarm that we have motivates us in the scientific community to help try to mitigate the impact of storms like Harvey and Irma and other storms that have occurred during this very active hurricane season. And the way that we do that is through research to improve our understanding, our ability to predict, and our ability to monitor extreme events such as tropical cyclones and their impacts. So today and tomorrow in these two webinars, we're going to focus on a broad cross-section of science that's being done both in NOAA and with partners outside of NOAA. And hopefully in these webinars, you're going to see that there are many scientific issues related to tropical cyclones that are relevant to the Climate Program Office, which is where we're located at NOAA. So we're going to hear about a variety of topics over these two webinars: how unusual Tropical Cyclone Harvey was, ongoing efforts to understand and accurately monitor flooding events, new modeling technologies coming along that can help with prediction, efforts that extend prediction capabilities beyond short weather timescales, and also how climate change interacts with events like these two hurricanes in particular. These webinars are part of a larger series of webinars that we run in the Modeling, Analysis, Predictions, and Projections program. We've been doing this, this is now our 7th year for this webinar series. And these are the first two webinars of this year's webinar series. It'll run usually through about June. And we hope that you'll decide to come back for more of these webinars. We're still planning the rest of the series, but we wanted to get these particular topics in as soon as possible while they're still, highly relevant, and there's a lot of attention being paid to the topic of these two hurricanes. You can sign up for our email list on the MAP website, and you can take a look at the archive of webinars over the last 6 years. We have recordings, YouTube videos, and also slides from the webinars. There are a lot of interesting topics on there. Some of these speakers have actually spoken before on similar topics, and so I'd encourage you to go and check that out. It's a really rich resource. Our program supports prediction, modeling, and analysis research that's focused on subseasonal and longer timescales, and this webinar series is an opportunity to present research that's funded by the program, as well as to discuss broader relevant research efforts in the community. Today's webinar is going to focus on climate attribution and hydrological impacts associated with these hurricanes, and tomorrow's webinar, which my colleague Heather Archambault is going to host, is going to focus on prediction across a variety of timescales, all the way from long weather to looking at seasonal timescales. So today we're going to hear from 5 speakers. We're going to hear first from Adam Sobel, who's at Columbia University, and he's going to talk a little bit about a National Academy's report that came out last year that discussed how to do attribution for extreme events. Second speakers and third speaker will be Tom Knutson and Sarah Kapnick, who are at NOAA's Geophysical Fluid Dynamics Laboratory, and they're going to talk about some ongoing NOAA efforts to understand the climate fingerprints that are on these two events in particular. John Nielsen Gammon is the third speaker. He's at Texas A&M University, which is pretty close geographically to where Harvey made landfall and where the precipitation maximum was from that event. John's also Texas's state climatologist, and he's going to talk a bit about the unprecedented nature of Hurricane Harvey and efforts to monitor its precipitation using radar data. Amir Agakuchek, who is at the University of California at Irvine, is going to speak fourth, and he's going to talk about a unique set of issues along coastal regions where you have flooding from precip events as well as flooding from sea level changes at the coastline, and that's in particular relevant for Harvey and what happened in Houston. And then our fifth speaker is Yulong Shah from the NOAA Environmental Modeling Center, and he's going to talk about how land monitoring efforts capture events like Harvey and Irma. And some of that work actually is inspired by drought, but here we're going to be talking about the wet side of that work for flooding events. So anyhow, I hope you enjoy the talks today, and you'll come back tomorrow and again for the webinar series. The way we run questions for this webinar series is by using the chat feature, so you can send me a chat message via the WebEx and let me know that you have a question. You can either type your question or you can just say, I have a question, and I'll unmute your line. And please submit your questions early and often because we'll go in the order that they're received. So Feel free even to submit questions while the speakers are talking. Only I will see the chat messages. And so that's about it. We're gonna go over to Adam first. So Adam, are you on the line?
Yes, I am.
Okay, great. I'm going to transfer control over to your computer, and then you can just share your screen with us and take it away.
Okay, thanks.
So Adam, if you go into the WebEx window and then the Quick Start tab and then the Share Screen button, you should be able to see
it. It just gave me the option now to click on. So
okay, great.
See if this works. Can you see it?
Yeah, it looks good. Yeah, take it away.
Okay. Right, thanks, Dan. So this talk is not a presentation of new scientific research. It's a combination of review and opinion. And I hope it's relevant. So I should say that I think the reason I got asked to do this is because I talked a lot to reporters in the media during these events, especially Harvey, and wrote a few things, and ended up in a lot of online discussions with colleagues in the scientific community as well. And this talk is really a sort of collection of thoughts based on that, as well as my understanding from participating in the National Academy study, which I'll describe in a moment. In the discussions with a lot of colleagues, between me and other scientists, as well as seeing what other scientists say in the media, you see this statement a lot: no one event can be attributed to climate change. This is something we all used to say. Some of us still do. And interpreted narrowly in a certain way, it's still true, but interpreted more broadly, it isn't. And so I want to say some things about that. My understanding of this subject is based on participating in the group that wrote this report that came out now about 18 months ago, spring of 2016, Attribution of Extreme Weather Events in the Context of Climate Change, by the National Academy of Sciences. And this report, like all the other Academy reports on every other topic, is really just a review of the primary literature. But it's, as you can tell from the title, to say we can't attribute events to climate change is not strictly true, because now there's a whole field of science that does exactly that, although how it does that is maybe a little more complicated than the most naive understandings might indicate. But you know, this field has come a long way in the last 10 years, and so I wanted to say something about it. The question is, what is attribution? I think most of you listening probably know this, but we draw the explicit connection between climate science as a whole and individual events. So the attribution science tries to say something about how a single event has something to do with climate change, or doesn't, depending on what the answer is. It's about quantifying the contributions of different causal factors to an event. Climate change is one of those causes. And a typical attribution study calculates how much climate change, or any other factor, but climate change is one we're interested in here, has affected some event's magnitude or its probability of occurrence. And so this was our task. I'm going to go through these sort of introductory slides very quickly, but it was to examine the science of doing this, to assess our understanding, how well can we do it, provide guidance about how robust the answers are, and identify future research priorities, the last of which I won't say anything about. This was the group. I don't want to dwell on it. It was chaired by Dave Titley. I'll just say there's a few people in this group who actually do attribution and are experts on it. The rest of us, including me, weren't. I don't do attribution studies, at least at this point in my career, but we worked in related areas. But you know, what I've learned is once you're on one of these panels, then you become visible and you get asked about it by reporters, and all of a sudden people think you're an expert. So what factors influence an extreme event? Any extreme event has many conditions going into it, and every event has a host of possible causes, and usually multiple actual causes. So every event, just by nature of the fact that it's extreme, it has to have something to do with large-scale circulation, the internal modes of variability, the specific weather pattern. A lot of things have to line up to make an event extreme, or it wouldn't be extreme. But human-caused climate change and other human factors, such as land use, can also play a role. I think this much is well known and obvious. One thing we try to emphasize very much in this report, and that comes up again and again in every conversation, is that can't answer the question of whether climate change caused a particular event, full stop. That's just an ill-posed question. The answer will never be yes, and often shouldn't be no either, but it's just a bad question. Natural variability is almost always a factor, maybe always would be a better statement. So we don't ask the question, was this event caused by climate change? When reporters ask us, we try to change the question. So better questions are events of this severity becoming more or less likely because of climate change, or to what extent could this storm have been more or less intense because of climate change, given other factors going into it being equal in two different climates. So just to say a couple of slides worth about how this is done, there's some methods that are primarily observational, and this is an example from one study, which was a very cold winter in Europe. And you can do it from observations if the observations are good enough. So in this case, there was this cold winter went with a certain circulation pattern with high pressure over the continent. And what these researchers did, the references is list the first author and year listed there. They looked at historical events that had the same circulation pattern, more as well as within some tolerance, historically and in recent years, and then how different are the temperatures given the same pattern. So that's trying to isolate the role of thermodynamics and greenhouse gases. And there's some difference, and so the authors attribute that to the human influence. This kind of thing can be done for kind of events where the observations are good enough and the link to temperature, which is the primary variable directly influenced by greenhouse gases, is direct enough. For some kinds of events, this kind of approach can't be done. The more broadly used approaches involve models, and the basic idea is that we have some model that can simulate the events of interest and then can also simulate climate change. And you run a real-world simulation of, say, many years, and you see how often that event occurs, and then you do it again with the human greenhouse gases removed, and you see how different is the probability of the event occurring. So the thing shown here is a flood in the UK, and what's shown are so-called return period curves, or it's a net stream runoff is what's plotted on the y-axis versus the occurrence frequency, the inverse of which is return period, logarithmic scale on the x-axis, and the blue line in each case is from a model estimate using the current climate, and then the other estimates, and these are from 4 different models in the 4 panels, are from different calculations of a pre-industrial control without human influence. And the observed level is the black line going across. So in all these simulations, to differing degrees, the simulations with the real current climate and the real greenhouse gases yield a shorter return period, a higher probability of this flooding event than would have happened pre-industrially. And this is sort of the basic idea. There are other approaches that are more highly conditional. I won't go into all the different ways this is done with coupled models, atmosphere only. Using specified SSTs is always an issue because you have to decide how you're going to specify them for the pre-industrial world. How you're going to take out the greenhouse gas emissions is always an issue. I will say something about highly conditioned simulations. This is a way that's not shown here in the slide where you basically run a weather forecast for a short period of time. You put in the initial conditions, like make Hurricane Harvey happen, and then you change the initial conditions just thermodynamically, like reduce the temperature uniformly in some way that you get from, say, climate model simulations, but keep the same dynamics in the initial conditions and see then what's the change in intensity or other characteristics of the storms. This is an approach that's more accessible for some kind of events that are hard to simulate in low-resolution climate models. Some events are more attributable than others. We can do this very differently for different kinds of events. It's the most reliable when there's sound physical principles involved. In other words, we understand the events and how they're related to climate. When we have evidence of a trend in long-term observations, that always increases our confidence. And if we're using models, then we want to believe that they can simulate the event well. And so all these things have to be examined when you look at any attribution study. Some events are more attributable than others. To be more specific, we have the highest confidence, I think it's safe to say, in how well we can attribute extreme heat and cold events. Hydrological drought, which includes the effect of evaporation on soil moisture, is maybe the next most, and heavy precipitation events because the temperature effect on water vapor is so strong, are next. At the bottom of the list, severe convective storms like tornadoes and hail and extratropical cyclones, we have little confidence in our ability to attribute those, either because of data issues or because what the climate effect even should be are not clear. Hurricanes are somewhere in between. They're challenging, but I think they're coming into range. We're starting to see a couple, and I think we'll see studies on Harvey and Irma. Maybe we're going to see one in the next talk. I know of at least one other that's in process. So I think it's at the leading edge of what the current methodology can do, but I think we're getting there. This is a table we came up with, not a table, a graphic we came up with for this report showing so our sort of judgment of how well we can do this. The x-axis is some qualitative measure of how well we understand how climate change affects this event, and then the y-axis measures how well we can actually do attribution, which is a function not only of understanding but also of technological things like how good the observations are and how good the models are. We left the upper right corner empty to indicate that every event can get better. You'll see that hurricanes are somewhere in the middle as far as understanding and a little below that in terms of attribution ability. I think that represents the limitations of the observational records and the need for high-resolution models to do hurricanes, as well as the fact that we don't understand, especially hurricane frequency, as well as we'd like to. If we were just talking about intensity and rainfall, though, I would rank it a little higher. So I want to say just a few words here about the effect of climate change on hurricanes. That's what the kind of events we're talking about today. And this is just based on a whole bunch of review papers and community reports that are briefly listed there. So this is my summary of it. And there's one figure from the IPCC at the bottom that I think I won't try to explain in detail, but it shows the expected changes percentage-wise compared to late 20th century, for the late 21st century, for the North Atlantic in several measures of hurricane activity. So, but I think what the science says is we're pretty confident that hurricane intensity, at least of the strongest storms, and definitely precipitation should increase with warming in a warming climate. And this comes from basic physics, water vapor for rainfall and potential intensity for wind, as well as I think virtually any plausible model, and there's some models that are not plausible for hurricanes, but any model that we take seriously is consistent with this. The frequency of tropical cyclones is currently thought more likely to decrease than increase in the future, at least globally, but that's very uncertain, much more than the first bullet. Models disagree on it, and they disagree even more when we go to individual basins. I think all things considered, it's reasonably likely that we should expect greater incidence of the most very extreme storms as measured by both wind and rain. I mean, it's somewhat of a competition between frequency and intensity, but I think if we look at the high end of the extremes, we're going to see more, and this is what Harvey and Irma are among the most extreme by some measures. Of course, sea level rise also increases coastal flooding hazard by starting the sea from just a higher level before any storm surge hits, and so that's actually a big factor. I'm not going to talk about it anymore here because it wasn't so much, at least with Harvey, wasn't the main issue, maybe with Irma to some extent. So there's a lot less agreement, and this comes up in attribution on whether we see these trends that we expect in the future already in observations. But maybe we don't ask the question right. Not to pick on Costin et al. 2013, I think it's actually a very good paper. It doesn't say anything wrong. It looks at trends in several data sets. This is a plot showing global trends over the last few decades, satellite era, from a homogenized data set that the authors made that's supposed to be good for climate studies and take out biases, and it's the trend in each quantile of hurricane activity. So it's, how are the most, least, and average and most intense storms increasing. You have positive trends over most of the upper range, except at the very top, which is pretty thin. With, not many storms, just one or two little quantiles. So most of this range we see positive trends, but they're not significant at 95%. The uncertain 95 range overlaps 0, so we tend to say we can't see these trends yet. I think this is maybe overly conservative because there's a huge amount of variability in hurricanes year to year, and we wouldn't necessarily expect to see modest trends yet, given all that noise. I don't want to explain this paper listed on the right in detail, but it's by Mike Mann and all, and I think it's one of a number of studies out there that's starting to look at this in a different way that doesn't give so much credence to the null hypothesis of 0 trend. If we know the trend we expect, why do we try to disprove a null hypothesis of 0 at 95%? Why don't we try to give the best answer that we can based on all the information? So this is sort of my concluding opinion. I have two slides of concluding opinion, which I'll try to say quickly. I think the standard frequentist approach to detection and attribution strongly privileges the null hypothesis of no trend and understates the real extent of our knowledge because we don't really think there should be no trend. So I wonder why we do this. And so I think the case is strong based on physics and models and other evidence that our future holds more storms like this than the past did, more very extreme storms. Now, exactly how far along we are in that change is debatable, but I think a lot of that is a signal-to-noise issue. Given the large natural variability, hurricanes are rare events, the data has problems, and that's a big part of the problem. And from the point of view of either mitigation or adaptation, it shouldn't matter that much. I mean, the greenhouse gases stay in the system a long time. Decisions we make now have a long time history. To some extent, the same is true of adaptation decisions. We know the direction we're heading. Exactly how well we can attribute a storm today, I don't think is really the critical question. The critical question is what policy decisions we make. And I think if we focus on attribution today, we're sort of missing the big picture. So just to summarize how I approach this when reporters ask me, when answering questions about the relationship between climate change and storms like these, which broke records for precipitation and wind intensity. In Irma's case, it was how long it remained at a very, very high intensity. I try to emphasize that these kinds of events are consistent with what our science predicts will be increasing risks in the warming climate, and to validate the very real policy concerns behind it. In other words, when reporters are asking us, they're asking us in part, should we be concerned about climate change? Should we be trying to reduce emissions because of the risks of storms like these? I think the answer is yes, and I try to emphasize that rather than focusing on whether we can eliminate the null hypothesis of no trend at 95%. So as my last comment, I'll just make the analogy. Imagine it was a terrorist attack. The CIA had a few lines of evidence, circumstantial but consistent, that somebody's planning an attack. And then you have a microphone that somebody's been managed to place in a room where the terrorists are planning the attack, we think. But it's a noisy room, and you can't hear what they're saying. So would we focus on that uncertainty and just try to reject the null hypothesis that there's nothing to worry about, or would we focus on all the other evidence? So I think that, I mean, the attribution studies will be done, and when those are done, we should take them seriously and see what they have to say. But in the absence of those, this is how I go about answering these questions. So I think I'll leave it there. I probably spoke too long.
No, that's great. That was actually perfectly 15 minutes, so thanks a lot, Adam. And I like that analogy at the end that we're commenting in the room here. That's really right on. So if folks have questions for Adam, please send them in via the chat. Again, you can just tell me you have a question, send me a chat message, say I have a question, or you can type your question in if you'd prefer. And Adam, we did indeed, we were watching your conversation on the map list, and that was part of the inspiration for inviting you, so you're correct in your uncovering of the reason, yeah. Anybody in the room here have a question for Adam? Adam, I think I'll wait a few seconds just to see if something comes in via the chat. Sometimes it takes a little while. Sure. Okay, well, I'm not seeing anything at the moment, but are you going to hang on for the rest of the webinar?
Yeah, sure. Yeah, sure.
Okay, great. So if anyone does have a question, you weren't able to send me a message in time, feel free to still send it, and we can always go back to Adam a little bit later in the webinar. All right, thanks a lot, Adam. Really appreciate it.
You're welcome. Thank you. Thank you.
Okay, so I'm going to transfer control over to GFDL now. So, Dale, are you on the line?
It's Tom Knutson here.
Oh, hi, Tom. How you doing?
Fine, thank you.
Okay, great. So I just transferred control over to the computer in the room there. And if you guys can share your screen, that'd be great.
Guess they're not seeing. You don't have it?
In the WebEx software, if you go to the Quick Start tab and then click Share Screen, we'll be able to see what you guys have up there. Okay, great. So Tom and Sarah, take it away.
Okay, thank you. So we get a lot of questions from the media about whether climate change is playing any role when we have big events like Harvey and Irma. So several of us have worked on some just putting down our thoughts on how to answer these questions, and this is I've worked with Sarah and also Marty Hurling on this. So today I'm just going to present some our summary of how we would approach this answering this kind of question. So I'll give the summary at the beginning, and then I'll spend the rest of my time sort of going through some of the technical details on why we're saying what we're saying. So, so the first thing about the first point is with Hurricane Harvey's record rainfall totals. These were primarily due to the storm basically stalling over the Houston area. There's no compelling evidence that we're aware of that climate change is making the occurrence of slowly moving landfalling hurricanes in that region, such as Harvey, either more or less likely. Now, Hurricane Irma was an exceptionally intense storm. It likely set a global record for the satellite era as the longest duration that a tropical cyclone has maintained surface wind speeds of at least 185 miles an hour. In terms of attribution, there is indirect evidence, at least, that the severity of some hurricane impacts, especially storm surge levels and rainfall rates, are being increased by anthropogenic climate change through increased sea level and atmospheric moisture. I think Adam was also mentioning these effects of sea level rise and moisture. However, increased hurricane surge levels and hurricane rainfall rates have not been clearly detected in the observed climate data. So this is that null hypothesis. Are we seeing a clear trend where we can reject the null hypothesis at the 0.05 level? Scientists expect that hurricanes will become more intense on average, based on our model simulations, in the Atlantic and globally as the climate continues to warm, but there's at present no clear observational evidence to date for this connection. Climate change is also expected to increase the global frequency of very intense storms like Harvey, Irma, and Maria in the future, but quantifying the effect remains difficult, and there's only low confidence for such an increase in the Atlantic basin. So these are our summary points, and now I'll try to cover some of the background behind these as we go forward. So I do think it's important to look, when we're talking about climate change effects on hurricanes, to look at the data to see if we see trends emerging in the data in long-term records. So these are some normalized indices of Atlantic hurricane activity and related indices. We see global, the top curve here is global mean temperature. These are all 5-year running means. So that shows a very clear rising trend, significant rising trend over time, similar to what we see in the tropical Atlantic, where we have a clear rising trend since 1880, a bit more multi-decadal variability superimposed on the case of the tropical Atlantic. When we look at raw hurricane counts in the Atlantic basin, that also shows a trend. However, if we look at U.S. landfalling hurricanes, this orange curve here is not showing any increase, significant increase over the century, since over the record we're showing here. Now, Gabe, Becky, and I looked at this discrepancy between U.S. landfalling and raw hurricane counts, and we decided to re-examine the hurricane record to see if we thought that this was a complete record or not, or were we missing storms in this earlier part of the record where the record has relatively low counts. And we think, based on our comparison of storm tracks with ship track density, that there were not enough ships in the Atlantic to actually observe all the hurricanes that likely occurred back in these earlier pre-satellite era. So we attempted to make some type of adjustment for this, and we came up with this adjusted hurricane count series, which no longer really has a significant trend, but it has bears more resemblance to the U.S. landfalling hurricane record. Now, this doesn't prove that there's no significant rising trend in hurricane counts, but at least I think it raises real questions about the validity of just using the raw data. And so to summarize, I would conclude from this that there's really not clear evidence of long-term increases in U.S. landfalling hurricane counts, or for that matter, basin-wide hurricane counts in the Atlantic basin, even though the temperatures are clearly rising. Global mean temperature and tropical sea surface temperatures are rising. Okay, so what about, so if there's no clear trend in the hurricane activity, what about some of the ingredients that came with these events? As Adam mentioned, sea level rise is important. And sea level rise is one where we have much more confidence that there's a rising trend. In fact, it's gone up about on the order of 8 inches or so since 1901. And IPCC concludes that it's very likely that there's a substantial anthropogenic contribution to global mean sea level rise. So we have rising sea level, partly attributable, very likely to anthropogenic forcing, and also the projected likely range of projected sea level rise under this high emission scenario for late 21st century is on the order of a half a meter to a meter. This is just the likely range, so substantial sea level rise projected for the future. And of course, models indicate that all else equal, when you have a hurricane, and in the case of higher sea level, it's going to just lead to higher storm surge levels. There are a number of studies that show this. It's a rather clear result. So I guess the answer then was, did climate change have any effect on hurricanes to date? I think the answer would be yes. All else equal, sea level rise is leading to higher storm surge levels in the hurricanes that do occur. What about other ingredients? So we have increased sea surface temperatures, not just globally, but also, as I mentioned, in the tropical Atlantic and even in the Gulf of Mexico. Now, this is a map showing the observed trend in surface temperature since 1901, so it's warming pretty much everywhere. And this is the trend we get from CMIP 5 historical runs, again showing warming pretty much everywhere, pretty bland pattern. And this is an assessment map, a summary assessment map, where we have red colors. That's where the warming trend is both detectable, so it's distinct from natural variability, and also it's consistent with the models. So we have detectable and attributable, at least partly attributable warming in these red regions, which include these many of the regions where Irma and Harvey and Maria track. So those hurricanes were tracking over regions where we've had detectable anthropogenic warming, at least according to the CMIP 5 model. So one of the ingredients, there are some ingredients that have changed due to anthropogenic climate change. Also, atmospheric moisture. So IPCC is concluding that there's medium confidence that there's an anthropogenic contribution to increased atmospheric specific humidity since 1973. So we have some confidence that atmospheric moisture levels are going up. We see it in the data, and it's been attributed in part, at least, to human anthropogenic forcing. There's also some evidence, at least in land regions, where there's sufficient observational coverage. There's at least medium confidence that anthropogenic forcing has contributed to a global scale intensification of heavy precipitation over the second half of the 20th century. So rainfall is getting heavier, and there seems to be some, at least medium confidence for an anthropogenic signal there. They're not saying we don't have the same, we can't say the same thing about hurricane precipitation. That has not yet been demonstrated to my knowledge in the observed data. We at least have model projections of tropical cyclone rainfall rates, and those are suggesting that hurricane rainfall rates will increase with climate warming, roughly by the same percentage as the increase in the environmental atmospheric moisture, and that goes up at about 7% for every 1 degree Celsius rise in sea surface temperature. I'll show a little bit more on that later. What about other, so we have these ingredients: sea level rise, warmer sea surface temperatures, more atmospheric moisture. We're pretty confident in those, anthropogenic contributions to those. There are some other ingredients where we're not quite so confident about the anthropogenic contribution, even though it can be important for tropical cyclone activity. For example, what about tropical upper tropospheric warming? Now that's something which actually acts to, in our models, actually acts to limit the amount of intensification of hurricanes we get with global warming. In our models, increased sea surface temperature makes hurricanes stronger, but when we have strong upper tropospheric warming, that moderates that increased intensity. So, okay, so in IPCC IR5, they did mention there's uncertainty about this change in whether there's been a change in upper tropospheric warming, low confidence in the tropics, in particular in the rate and vertical structure of those changes. Also, there's uncertainty about the Hadley cell. It appears to have widened, but the magnitude of the widening is very uncertain. So circulation changes are rather uncertain. Now here are our tropical cyclone rainfall rates from our simulations. They go up about 10% to 15% on average by the end of the 21st century. This is showing the percentage change in rainfall rates in all different basins. The blue line is what we would expect the percentage increase in rainfall to be just based on this 7% per degree Celsius. And we see that the model's precipitation changes line up pretty well with this 7%. Here at the Northeast Pacific, it's a little more, but in general, it's lining up pretty well with the 7%. So more atmospheric water vapor in our models leads to higher rainfall rates. This is the intensification we see in the models. This is a histogram of maximum wind speed. So we see some, at least a small intensification. It's about 4% on average globally by the end of the 21st century in intensities of storms in a warmer climate. This is based on downscaling, dynamical downscaling simulations. And again, we don't see this clearly yet in the data. This is our expectation of what will happen over the 21st century. We're seeing about a 28% increase in category 4 or 5 frequency, 35% increase in category 4 or 5 days globally in our simulations. We see that the changes seem to be biggest here in this is the warm scenario, this is the present day scenario. The changes seem to be biggest here, say, in the Northeast Pacific basin. In the Atlantic basin, things are a little bit more complicated because we do see some indication of increases in category 4 or 5 hurricane tracks in a warmer climate. This is the present day, and these are various warm scenarios compared to the present day. All of them are showing more storms, more category 4 and 5 than the present day, but the significance levels here are sort of marginal, in some cases not quite statistically significant. So there's sort of marginal significance coming out of our model studies. That's because there's a competition between fewer storms overall, increases of intensity, and it's sort of, we get some indication of an increase in the most intense storms. So I'm going to let Sarah finish up here.
Okay, thank you for bearing with us with the changeover. So as Adam was saying, in the question of the attribution, in a way it's also an ill-posed question of just, can you attribute this to climate change right now? What do we expect in the future? Because we could actually think about these questions also on shorter timescales. And so one of the ways that we've been trying to communicate this issue as well after these storms is that there's a lot of work that's being done also on the seasonal prediction of cyclones. So CPC puts out an outlook for the number of storms in the Atlantic, but what we're doing at GFCL that is purely research-based, this is not operational, is right now we're trying to understand and better understand, can we know how many landfalling storms there will be before the storm season even starts? So in the top, we have this 50-kilometer model that has been developed that actually has pretty good ability to understand how many landfalling storms you should expect at the beginning of the season using the dynamic model, coupled model. And we also have another experimental 25-kilometer version that similarly has good scale for the United States and the Caribbean. So with this, we're actively trying to better understand what are the time scales that we can also understand how many storms that we should have to build resiliency. Also, stepping back from just the hurricane problem, with Harvey, it was an extreme rainfall issue. So last year, there was a study that was conducted by a number of us here that was looking at can you attribute Louisiana rainfall event, which is in the central Gulf Coast, to climate change. And so this actually, in the bottom left corner of the quadrant that we had, there's a pointer, you actually do have a portion of Houston. So we looked at these extreme rainfall events and tried to understand extreme rainfall events in the present climate and the past climate. And from our understanding using all available modeling data and observations is that you actually have an increase in the likelihood of these events. Now, the amazing part of having global climate models that are high resolution that actually get extreme events is you can produce hundreds of thousands of years of data to try and understand what the probabilities of these events are and how they change over time. And only with those really long data sets can you start to have lower and lower bounds on the range of your expected changes that you have. So with observations and short records, we have these large ranges of potential for climate change, but with the models, we start, because you have more data, you can actually reduce some of your confidence intervals. Now, more importantly, broadly, we need to understand how these models capture extremes and capture the changes in extremes. So looking at precipitation as an example, we've used a different suite of different resolutions of models at 250 and 25 kilometers, as well as looked at seasons of different types of precipitation extremes. So I'm showing here is a 5-year returning event and how it changes in our climate change. So from this, depending on the model that you choose, depending on the season that you choose, you either have increases or decreases in the likelihood of extreme precipitation under 2 times CO2. So it's really important to realize that these changes that we see in our calculations of extremes under different climates relates to resolution and the season. So we need a lot more work to be done to understand why these differences exist and to really look for building models to answer these questions. So we're working on this very actively right now. I know SJ Lynn will talk tomorrow about a vision of the future for some of the modeling. But with these questions that we're getting, there is a bit of uncertainty, and we need to better address these questions and really address the questions that people are answering in advance of these events as well. So then we have the answers when the events happen. So we have some summary points. So they're the same from the overall talk, and we can answer any questions now if there's time, or we'll wait to the end.
Okay, great. Thank you, Tom and Sarah. There is a question. You give me a moment to bring it up. Bear with me. Okay, let's see. I haven't read through this question yet, so I'm not sure how it's going to come out, but this person asked about the addition of data to the number of hurricanes occurring in the early part of the century because there were no ships to observe them. How did you determine the number of hurricanes to add, and what was the justification for that number?
Yeah, so that we have a couple of publications on that in Journal of Climate. It's really just an educated guess. So first, we assumed that storms in the satellite era had actually occurred back in the, say, 1900, 1910 era and so forth. And we know from observations ship tracks over time during that time period. So basically just simulated whether during a storm's lifetime it would have gotten close enough to a ship for the ship to actually have observed gale force winds. And so you run, it's basically a simulation, and you see how many of these hypothetical storms would slip through the cracks and not be observed, given the ship track density, which was fairly sparse over some regions of the open Atlantic. See, the issue is that in the satellite era, we have a very good ability to see all the hurricanes that are occurring in the basin. Before, in the pre-satellite era, though, we were basically sort of flying blind. Either if a storm happened out in the far reaches of open waters of the Atlantic basin, if it encountered land somewhere, then it would be detected. If it encountered some ship by chance, it could be detected. Of course, the ships were not trying to encounter storms. They were more likely trying to avoid them. So anyway, so our ability to actually monitor the total amount of storm activity in the Atlantic basin was limited in the pre-satellite era. And based on our assessment of the the shipping track density, we just don't think there were enough, that the ship track density was high enough to observe all the storms. If hypothetically, say, modern era storms would have occurred. So then we sort of played off all the modern era storms against the historical record of ship tracks and built up a probability density distribution of the expected number of missed storms, which is just a statistical distribution, and then we're just reporting the mean of that distribution here. So it's a very sort of what if hypothetical calculation, not a precise science. But then after you take what we found and then compare back to the U.S. landfalling record, it is at least intriguing that even after all this adjustment, that we basically end up getting back to something closer to what the U.S. landfalling record looks like with our adjusted record. So our hypothesis then is that the actual record of basin-wide hurricane counts is really, in terms of a long-term trend, is more likely to resemble something more like the U.S. landfalling record than this raw hurricane count, where we think this earlier part of the record is particularly suspect. And we have some other indications of that too as well. It turns out that a lot of the storms in the latter part of the record were fairly short, only last less than 2 days. And we have almost none of these short-lived storms in the early part of the record. That's the kind of symptom you might expect to see if you had a very short-lived storm in the early part of the record way out in the basin. That's the kind of storm you would expect to have missed and not be in the database. So does that answer the question, or I can go into more detail if you like?
Hi, Tom. Thank you so much for that answer. There was kind of a related question to elaborate a bit on, if you look at the same statistics for major hurricanes or most intense storm activity by other metrics, and Adam touched on it a little bit, but I think, would you be willing to shed some insight from your perspective on that question?
I'm sorry, could you repeat the question?
Yeah, sure. It's kind of like similar to what you were just addressing, but focused on major hurricanes like Cat 4, Cat 5, or other metrics of storm intensity.
Yeah, that's a great question, because I notice in this time series, I'm not showing any intensity data. I know Adam showed some intensity data going back to 1980 or so. We have some real concerns about intensity too, like our ability to actually monitor the number of Category 4 and 5 hurricanes out in the open parts of the basin, again in the pre-satellite era. And I know that I believe his name's Andrew Hagan and Chris Lancey have done some work on this, looking at our ability to actually determine the intensity of a hurricane using observational capabilities of the past. So again, they did some sort of what-if types of examination of this issue and conclude that because of changes in our observing capabilities, we did not have the capability of detecting in the open, out in the open Atlantic, something like a Category 4 or 5 in the same way that we can do that with in the modern era, where we have many more types of measurement platforms that we can rely on. So for that reason, we are very hesitant to, say, plot a time series of Category 4, 5 hurricanes, say, going back to 1900. It clearly would have a trend, but we don't really, would not really place too much credence in the trend in the raw data at this point until one expends a fair amount of energy in going through and making sure that you're really comparing apples to apples, that the data that you're looking at in the early part of the record can really be compared quantitatively to the data in the latter part of the record. So this is a real challenge for climate science, I think, because long-term records are essential for demonstrating whether we have trends which are clearly different compared to natural variability. It gets back a little bit to this point about the rejecting the null hypothesis. I think when one can reject the null hypothesis, when one can say that there is a change which is clearly different from natural variability in the climate system, and it's consistent with what models are simulating, that gives us a lot more confidence in future projections with those same models. So I think that this is a very important activity of looking at the past data and looking for significant trends, looking for evidence of things which are clearly distinguishable from natural variability. That's why we have so much confidence, I think, in the projection of future global warming, global mean temperature, because when you look at the past record of global mean temperature, there's a very clear rising trend, and it's consistent with models. So we have that detectable, attributable signal, and that gives us then a lot more confidence in the future projection than in the case, say, for Category 4 or 5 hurricanes, where we can't really rely on having that past record, which is really supporting what we're saying about the future projection. So it leads, I think, ultimately to lower confidence in a projection of say, future Cat 4 or 5 hurricane activity, because we don't have the supporting evidence of the clearly distinguishable long-term trend like we do for global mean temperature.
Okay, Tom, thanks a lot for the answer to that question. And I don't have any other questions. So thanks for you and Sarah to speak today. As Sarah mentioned, there's a talk tomorrow from S.J. Lin, and he's going to pick up a little bit more on some of the GFDL model development and prediction activities. So thank you for that plug for the talk tomorrow. And thanks both for joining. Okay, the next speaker is John Nielsen-Gammon. John, are you on the line?
Yes, I am.
Great. I just transferred control over to your computer, so if you go to the quick, oh, you beat me to it.
Sorry.
That's great. You're a pro. Okay, looks great, so take it away.
All right, so I'm going to talk about the exceptional nature of Harvey's rainfall, which is of intrinsic interest for a couple of reasons, besides scientific. First, weather geeks like myself love record-setting events and keeping track of statistics of them, but more important societally, we design our cities and infrastructure to withstand events at a certain risk level, and events like this that come along, as I will show you, have the potential for telling us that we haven't actually designed things as resilient as we thought we had. Anyhow, I'm going to use for the rainfall data the real-time daily analyses produced by the River Forecast Centers. In this part of the country, it's the West Gulf River Forecast Center, which is hosted by the same building as the Southern Region of the National Weather Service. It's a branch of the Weather Service, which of course is part of NOAA. This is 24 hours ending the morning of August 25th, at which point NOAA was still out in the Gulf of Mexico. It made landfall in the evening of August 25th. I'll just point out the color scale is designed to represent fine gradations of rainfall totals ranging from 0 to 3 or 4 inches, and it gets a bit coarser after that. And that means we can't see very well the extreme intensity of Harvey on these particular maps. This is covering the time it made landfall. You can see most of the intense rainfall was associated with the inner rain bands and eye of Harvey, but there was also some precipitation farther toward the northeast, towards Houston. The next day's precipitation, Harvey had moved inland and was still producing a lot of rainfall near its center, southeast of Austin, Texas, but at this point, Houston was receiving its initial major flooding. Go forward another 24 hours, we still have widespread areas of 10-plus inches of rainfall extending across a broad swath from west of Houston to Louisiana, which also did get a bit of flooding of their own. The next 24 hours, still widespread intensive rainfall in southeast Texas. Next 24 hours, the same thing, and finally the storm made landfall again in Louisiana, is moving off to the northeast. So I'll just quickly loop back and forward again over this so you can get a sense of how not only was it producing 10 inches of rain per day in widespread areas, but because the storm was moving slowly, that was happening in the same location for several days at a time. There's not, as far as I know, much work on what makes a particular hurricane produce a lot of rainfall wherever it happens to be, but as was mentioned before, one of the key aspects of Harvey was the fact that it moved so slowly so that the rainfall it did produce was occurring over roughly the same area for several days. And while it was onshore, it was still tapping into deep tropical moisture, which also contributed to its ability to produce lots of rainfall even after it had weakened to tropical storm status. I want to show you an example of maps that we produced. The purpose of this was for monitoring drought. So this is work funded by NOAA and by the USDA, and it's a plot of standardized precipitation index. Negative values indicate drier than normal. -1 means 1 standard deviation below normal. +1 is 1 standard deviation above normal. And this is where Texas was sitting as of late August in terms of precipitation over a preceding 12-month period. As you can see, for the most part, the eastern half of the state was right around the 0 mark. 2 weeks later, we had areas of southeast Texas, including Houston and Beaumont, that were in the greater than +3 category, which means the equivalent of 3 standard deviations above normal, which, of course, is something that should happen only extremely rarely, but that's the sort of thing that happened last month. I think people who are not from Texas have difficulty of understanding the spatial scale of these events. So here I'm showing you the total rainfall from Hurricane Harvey and a few days surrounding. The white now corresponds to 20 inches or more of precipitation. And you see 20 inches or more extending from almost Austin across Houston and Beaumont into Louisiana. Now what I'm going to do is move that precipitation map over the northeastern United States. And what we see is the area affected is equivalent to the area all the way from Boston to New York City, with 20 inches of rain in Philadelphia thrown in for good measure. So this was really an impressive amount of rainfall over a large area. So it's not just the highest rainfall total, which is interesting statistically, but also since the amount of rain that falls over a given area is what produces flooding, I want to examine how Harvey stacks up against previous storms in that regard. So what I have plotted here are my best estimate of the historical 10 most intense rainstorms in terms of average amount of rainfall produced over a 10,000 square mile area over a 5-day period. And what we see is a few storms that will be familiar to people, like the flood last year in Louisiana, which was mentioned earlier, the Hurricane Floyd, which hit North Carolina. The top two that I have plotted on this diagram are Hurricane Beulah, which made landfall in South Texas and was also notable for being the greatest tornado producer. And then a storm back in 1899, which produced widespread flooding. We don't have a lot of gauges on that, so the exact value for the rainfall is a bit uncertain. But I've hidden the bar for Harvey, so that let me add for you Harvey's total. And it is literally off the charts. The average rainfall over the wettest 10,000 square miles was approximately 33 inches, which breaks the previous record by about 50%. And you can see that you generally would break a record by a small amount. It's it's quite remarkable how far above previous events this is. Now, of course, I've cherry-picked this. I've picked the most dramatic example of Harvey being a record breaker. So let's actually look at a much broader range of durations and area sizes. And in fact, for just about every area you can consider, from 1,000 square miles to 50,000 square miles, from 2 days to 5 days, Harvey appears to be the new record holder. For those smaller areas, that's definitely true for the central and eastern United States. The larger areas is true for the entire United States. The one storm that makes it onto this table outside of Harvey was a tropical event in Louisiana back in 1940. So you can pick your record, Harvey holds it. Here's another plot of what we call depth area duration. So the duration here is 5 days again. The area is now 1,777 square miles. We get a slightly different listing of storms, but still Harvey over on the left is the winner, except in Harvey's case, I have not chosen the wettest 1,777 square miles. I actually picked that number, 1,777 square miles, because that's the area of Harris County, county in which Houston is located. And that's the bar that's plotted there. So the rainfall in Harris County exceeded the rainfall in any other storm over any comparable area that we know of. So in other words, you could have taken the wettest storm on record for an area the size of Harris County, had it perfectly target Houston, and it still wouldn't produce as much rain as Harvey produced. One way we look, so certainly it's going to be an exceptional event, but one way we design infrastructure that needs to be fail-safe, for example, things like dam spillways, which need to be able to withstand however much water might conceivably need to be flowing over the dam or around the dam without causing the dam to collapse. Engineers use something called probable maximum precipitation, which is it's designed to be, well, it's defined to be the greatest amount that's theoretically possible, but atmospheric scientists don't have a theory for how much rain could theoretically fall. So what's done in practice is take the wettest storms ever, figure out where they could conceivably have occurred, figure out how much moisture inflow could conceivably have been present, and estimate the upper bound based on that. And this is a plot for probable maximum precipitation over different area sizes for 2 days and 3 days. Harvey is the line with the round dots, and the previously estimated probable maximum precipitation is the squares. And what we see for the 3-day total, 72 hours in particular, for a range of area sizes, Harvey matches or even exceeds what was thought to be the probable maximum precipitation in southeast Texas. So in a sense, the rainfall was actually inconceivably intense with this event. Lastly, I want to make a couple of comments on climate change's impact on Harvey. You've heard some good background on this issue from the previous two speakers. We don't know whether Harvey's slow motion was affected by climate change one way or the other. There are reasons that would point in both directions, so to speak. We don't know to what extent Harvey's intensity was affected by climate change, and that may have played a role in how long it lasted. But we have solid evidence that extreme rainfall is increasing because of climate change in various parts of the world, including the United States. And for me, the null hypothesis is if extreme rainfall is increasing, then we should assume that extreme rainfall in hurricanes is increasing similarly. And we do have model results, as you've seen, that are consistent with that. So with ocean temperatures in the Gulf of Mexico, say, having warmed about a degree Celsius compared to pre-industrial. We translate that into a 7% increase of rainfall, which by the way is consistent with what's been observed in Texas for extreme rainfall increases in general. That 7% looks like this on this chart. And there are lots of different ways that this can be interpreted or spun. So, for example, if you ask, was Harvey's rainfall record-setting because of climate change? For those aspects we know about, no, it would have been a copious amount of rainfall even without that additional 7%. Was the magnitude affected by climate change? Apparently yes, for the reasons I described. And again, the estimate here is 7% increase in magnitude. Was the odds or risk of an event such as Harvey affected by climate change? I have not assessed that, but I imagine that's going to be a fun question because it may be that Harvey was such an unusual event that even the folks that do attribution with thousands of model simulations may not actually have an event as intense as Harvey. And when you start getting to the really unusual events, a small increase in magnitude translates into a very large change in the odds. So I would not be surprised, for example, if you translate this 7% increase of rainfall to odds of getting that much rain, it might be more like something like a 10 times or 100 times as likely because of climate change as without it. But ultimately what matters is the damage produced by the storm. And damage tends to increase non-linearly with intensity. For example, we design most of our infrastructure to be outside the 100-year floodplain. So if you get a flood, even if it's not what we call a 100-year event, it wouldn't cause a lot of damage compared to something that exceeds that value. So just for illustrative purposes, I've suggested what a nonlinear increase of damage might look like. And from this, it's easy to at least imagine that a small increase of rainfall from a very extreme event can be very impactful. So my take-home message is here, Harvey's rainfall was exceptional by just about any definition of the word exceptional. The flooding was disastrous, primarily because Harvey's rainfall was exceptional. There's talk about, and people have written about how development may have contributed to flooding, how impervious soils or soil that doesn't absorb moisture much may have contributed to the flooding. Those sorts of factors tend to be accounted for in design and assessment of risk. So if you had someplace that, for example, that had soil which absorbed water directly, that had plenty of reservoir protection, it would still be designed to withstand rare events, but not exceptional events like Harvey. So Harvey would produce that disastrous rainfall anywhere there was infrastructure to impact. And as I mentioned, in an important sense for public safety, Harvey may have produced more rain than was thought to be possible. In that sense, we're already at probable maximum precipitation with Harvey, and as temperatures continue to rise, including sea surface temperatures, scientific expectation is extreme rainfall amounts will continue to rise also, which means we're getting new possibilities for what sort of flooding events, what sort of rainfall the atmosphere is capable of producing. So that's all I have, and I'll be happy to answer questions.
Thanks, John. That was really very interesting. For folks on the line, again, send a chat message. Let me know if you have a question. I can unmute your line, or you can type your question in. I haven't received anything yet. Is there anything in the room? Anyone have a question in the room for John? I think while people mull it over, John, I was wondering if you have information on the rainfall rates and whether those were unusual within some of the bands, some of the really heavy bands that came through in Harvey.
We saw rainfall rates of, I think, up to 6 inches an hour, which in lots of places would be really impressive. But we had a storm in October of 2015 near Austin that produced a 9-inch per hour rainfall rate. So Harvey wasn't off the chart so much for the rate of rainfall. It was just a relatively large rate of rainfall occurring over the same place for a long period of time.
Yeah. Okay, thanks. I haven't seen anything come in through the chat yet. Anyone in the room come up with a question for John? Okay, John, are you going to be able to hang out for the rest of the time?
Yeah, sure.
Okay, so if there's another question, maybe I'll come back to you, and if you're online typing, just let me know. Oh, you know, actually somebody just popped a question in. Okay, so let's see, this question is, from a meteorological perspective, can you discuss the lack of any steering winds that might have picked Harvey up from the Gulf and moved it inland?
Sure. In normal circumstances, climatologically, storms, by the time they're making landfall in Texas, they obviously tend to be moving toward the northwest because of the coastal orientation. And then they'll tend to move toward the north and toward the northeast with time. The northward component is partly background winds and partly what we call beta drift, the fact that the hurricane itself is affecting its environment and will automatically tend to move away from the equator in the absence of anything affecting it. In the case of Harvey, we had in the jet stream a ridge over the western United States and a trough over the eastern United States, so that the middle tropospheric winds were from the northwest, weak from the northwest, which, as it happens, was just enough to cancel out the tendency of Harvey to drift to the northwest in the absence of winds. And let me use that as a jumping off point to just expand briefly on whether climate change affected Harvey's motion. One reason for suspecting that climate change might have made Harvey more likely to stall is research which is still somewhat controversial, but indicates that summertime jet stream patterns are becoming more likely to be locked into place and be stationary, which would allow for, say, stalling winds to persist for a longer period of time if that research is correct. But on the other hand, you heard earlier that the tropical belt is expanding northward, which one measure of that is the jet stream position on average is farther north, which means that in that sense, climate change is making the jet stream less likely to interact with a storm that's at the latitude of, say, 25 or 30 degrees. So that's why I say that the impact of climate change on Harvey's motion is even the direction of that impact is not clear.
Okay, thanks, John. That was an interesting answer. There was another question that came in that's on a little bit of a different track, but this person is wondering whether in your role as a state climatologist, do you feel that you'll be able to play a role in helping communities impacted by Harvey move forward with resiliency measures?
Yeah, I certainly hope to be playing a role in that. For starters, I'm going to be working on sharing information on the wide range of rainfall data collected during Harvey, including by just private citizens that send in data to Weather Underground or CoCoRaHS or that sort of thing, so that we can really pin down the rainfall totals as exactly as possible, which in turn will enable the hydrologic models to simulate flooding as accurately as possible and be able to thereby represent future storms and future possibilities accurately. Beyond that, another interesting question, of course, is the future trend of extreme rainfall. And Houston itself has experienced several floods in recent years. And some preliminary work I've done indicates that the trend in Houston is much larger than the trend in most other parts of Texas. And, you know, you could hypothesize that maybe it's because it's a big city, but we don't see the same trends in San Antonio or Dallas. You could hypothesize, well, maybe it's being close to the coast, but we don't see the same trends in other coastal locations. So that seems to be basically bad luck in a sense, or natural variability, as scientists prefer to call it. But that is important going forward because if you're predicting extreme rainfall to increase and therefore flooding susceptibility to increase, you have to say increase relative to what? And we need to figure out what's the appropriate baseline, what's the appropriate reference period, given that extreme rainfall historically has been so variable. So that's another issue I hope to look at.
Yes, there's one question here in the room from Anarita. Anarita, go ahead.
Hi, I was just wondering whether you looked at other aspects of circulation associated to Harvey, and in particular whether you had looked at like wind gusts and whether there was anything exceptional there that could have added to the impacts of rainfall.
No, I haven't looked at the winds in particular. One thing we're going to be trying to pin down for the rain gauges, for example, is whether they're mounted in a level fashion, because the prevailing wind direction for several days was from the northeast and the southeast because of the storm, so a gauge tilted toward the east would potentially pick up a foot more rain than one that's slightly tilted toward the west. So the wind is going to affect the measurement on the one hand. I don't know to what extent the wind caused the rain, except for the fact that there was clearly, let me go back to the rainfall map, there's clearly a connection between the rainfall distribution and the coastline. Winds coming from water to land experience an increase of surface friction, and so there's convergence at the coast. And so I would imagine that the fact that we had onshore flow going on, in addition to being able to bring in and replenish the moisture, was also causing there to be locally enhanced rainfall because of that frictional effect.
Okay, great, John. Thanks for fielding so many questions as well. There was one more question that came in, but I think in the interest of time, I'm going to move on. And if we have a little bit of time later, maybe I'll come back with that, if that's okay with you.
Okay, sure.
Okay, great. Thanks a lot, John. So next up is Amir Agakuchek. Amir, are you on the line?
Yes, I'm here. Can you hear me?
Okay, great. Yeah, you're a little bit muted. I don't know if you can maybe get closer to a microphone.
Is it better now?
Yeah, it's a little bit better. Yeah, thanks. And then in WebEx, you should go to the Quick Start tab, and then there should be a share screen button there so you can show us your slides.
Can you see my slide?
Yeah, it looks good.
Right.
Okay, go ahead, Amir.
All right. So today I'm going to talk about coastal flood risk analysis, considering multiple drivers, ocean and terrestrial or fluvial flooding. And this is about a paper that came out on the day Houston got flooded. So in coastal areas, you know already that there are multiple drivers. The two key drivers are surge, basically ocean flooding, and hurricanes involve a lot of rain, so you get also inland flooding, and they interact at the coastal areas. And the higher the sea level or surge, the smaller will be the gradient between fluvial and ocean water level, and the higher will be the backwater, and of course more flooded areas, more inundated areas, you expect. But how do we handle flood risk now in coastal areas? So if you look at USGS guidelines, we fit a distribution function, typically log Pearson type 3 to stream flows, and we create curves like this, flood frequency curves. And we have also guidelines for ocean flood analysis from FEMA and other places, and even you feed it GEV distribution to ocean water levels. And again, from that, you do sort of frequency analysis on, total water height, or even surge or combined. But in both cases, we ignore the interactions between the two drivers. again, we know that physically the two are related, and we understand the relationship. We can even model that using high resolution flood models with ocean boundary conditions. But when it comes to formal flood risk analysis, then we kind of ignore the interaction between the two. So the goal of our study was to come up with a way to handle this sort of compounding effect of ocean and terrestrial flooding. So a quick definition of compound events, and this definition comes from IPCC mainly and 2 follow-up papers. When you have 2 extreme events happening at the same time, or you have 2 non-extreme events that happen at the same time, but they have an extreme impact. So you can have, let's say, moderate flooding, terrestrial flooding, moderate ocean flooding, but when they happen together, it can lead to extreme impact in coastal areas. The same with droughts and heat waves and many other, events that have multiple drivers. So basically considering events with multiple drivers, but there are different types of them. Okay, now in our study, we looked at different major basins, and we looked at this compounding effect and trying to understand the relationships and how the flood risk will change if you consider multiple drivers. So when you want to look at multiple drivers, you need to have a kind of definition for hazard. There are many different types already in the literature. For example, the left one is known as the Kendall hazard scenario, where you have a threshold. You have 2 drivers. In this case, let's say discharge on the x-axis, water level on the y-axis. You need to have a hazard scenario, and then you do sort of frequency analysis on values that exceed, a critical threshold. On the right, there is what we call it the OR hazard scenarios, where you have 2 thresholds. Do you see my cursor?
We do.
So, yes, so this is, let's say, your water level threshold, which is critical, let's say seawall level, and this is a critical threshold for discharge, and anything that exceeds above, is a critical event. And this is usually, it's called OR hazard, and it's used when one driver alone can cause problems. And this is the case usually in the coastal flooding. Either one can cause, serious flooding. So we went with the OR hazard scenario, and we thought a lot about how to communicate this type of risk information. John mentioned engineers and design guidelines. In engineering design, we use this notion of failure probability, and it is mainly used in a kind of univariate sense. And here is the univariate equation for failure probability, and T is design lifetime. Let's say you're building a levee for 50 years or 100 years, and P is probability of occurrence, and this gives you, probability of failure. Failure doesn't necessarily mean physical failure. Let's say you have a levee and you don't want the water to get more than 10 feet from the base, because that's your, let's say, freeboard threshold. Any exceedance above that, it's called failure, even if it doesn't lead to physical failure. So in our study, we sort of extended the failure probability, what is used mainly for one hazard at the time, to a kind of multivariate, multi-hazard scenario, where you have multiple drivers. In case of coastal flooding, 2 drivers, ocean and terrestrial flooding. So this is the general equation, and this is a multivariate model. You need to combine 2 different drivers. So conceptually, this is how it works here in this figure. You see that if you have one single hazard, let's say terrestrial flooding, and you do sort of frequency analysis with USGS guidelines for a particular structure, you will get a curve like this, and the y-axis is failure probability, and the x-axis is design lifetime, 30 years, 40 years or so. And the bivariate cases where you have multiple drivers, in this case. And in our study, I'll present some results for different locations. We also consider sea level rise for the failure probability analysis. Imagine if we get the same event in the future, the same sort of terrestrial flooding, the same amount of precipitation and surge, but sea level is, let's say, 2 feet higher, the flood will be worse, a lot worse in coastal area, of course, right? So we wanted to also be able to account for the effect of sea level rise in this sort of compounding flood analysis. So here are some results. On the top left, you will see this sort of conceptual figure for this sort of ore hazard analysis, or sorry, compound extreme analysis. And you have some observations. These are the dots, and you have here the blue dashed line here is 20-year coastal flood level. So it's sort of, let's say this is a kind of a somewhat extreme threshold, and 20-year fluvial flow. Again, these two are not that extreme, but it's still relevant for drainage and design and so forth. And the red line here is the corresponding bivariate 20-year extreme event, and you consider 2 events. And areas A, B, C are areas that we are interested in. So exceedances above these 2 red and green lines are sort of critical events for us. Now, if you look at these 3 figures are for different locations. The first one is Philadelphia, second one San Francisco, and third one is Washington, D.C. So if you look at this one, for example, again, this is 20-year water level event, and this one is 20-year terrestrial flooding or fluvial flooding. And you can see, if you look at the intersection, the ore hazard scenario tells you, if you consider the compounding effect, that this point is a 13-year event. Although, again, if you look at the univariate case, you're looking at 20-year event. So this indicates that if you consider multiple hazards, the event field is more likely to happen. In other words, what you consider as 20-year events, when you consider the compounding effect, can happen, on average once in every 13 years. So it's almost twice more likely, almost a little less than that. So this is a way to account for multiple drivers, and depending on the relationship between coastal water level and terrestrial flood data, this relationship could be weaker or stronger. So in case of Washington, D.C., for example, univariate 20-year event corresponds to, 16-year compound extreme event, considering the interaction between 2 different drivers. I don't want to go through all the details. In the paper that's available on my website, there is a 70-page long supplementary information with different definitions. There was an independence assumption that we have included. I don't want to go through all the details, but I'll be happy to answer any questions. And about the sea level rise, again, we did this analysis for different places using first univariate, let's say just terrestrial flooding, looking at failure probability on the y-axis and lifetime in the x-axis. Okay. We looked at the compound extreme event or ore hazard scenario, the red line, and almost in all cases, the failure probability increases when you consider multiple drivers. Again, this is what we expect, but we try to put numbers on this sort of compound events and how they change the risk of failure in coastal areas. And then the sea level rise, once you have the model, then you can use different sea level rise projections and see how the coastal flooding changes considering different sea level rise scenarios. In this case, Washington, D.C., the purple line here is using sea level rise scenarios from Pope et al. That consider future projections and also correct for local land subsidence and things like that. So this means that even if we don't consider changes in current terrestrial flooding, if you just add future sea level rise scenarios, the failure probability increases significantly. So the purple line, the solid line, is from the median of future simulations centered around 2030, and then the two dashed lines are the 5 and 95% bounds. So this framework allows you to consider changes in flood risk considering different sea level rise scenarios. So we've done this for different locations around the country. This one is the top left is Houston, Texas. And you can see that there's a big difference between univariate and bivariate case. This indicates that the compounding effect, the interaction between the two drivers is actually pretty significant. And then you add a sea level rise, again, that increases more. And one more thing, again, you see in some cases failure probability reaches to 1. Again, it does not mean physical failure of whatever you're designing or at whatever level you're considering. It means that it's likely that it will exceed that particular threshold, whatever it is, in this case, 20-year event, 20-year compound event. So in summary, concurrent coastal flood frequency analysis, current coastal flood frequency analysis not really address this sort of compounding effect, multiple drivers, and we believe it is really, really important if you want to provide reasonable coastal flood risk information. And if we go with the current univariate methods, we may underestimate the risk of flooding. And still, we believe there are research gaps. In our paper, we propose a sort of theoretical model to address terrestrial and coastal flooding, but still there is theoretical gap for detection and frequency analysis of compound events. In some cases, there are more than 2 drivers. We need more development in this area, and there are many different types of compound events that happen in different scales. We have drought and heat waves and many more. And in addition to that, John also mentioned development and human activities like urbanization. They play a role, and they can also have this kind of compounding effect, but it's not easy to bring them in flood risk analysis, and that requires a lot of research. That's what we're doing right now. And if you're interested about the theory and the method, it's available. You've used this multivariate copula analysis toolbox. It's available on my website, the source code, and these are the 2 developers. And there is a paper that explains model fitting and all the theoretical parts, theoretical analysis. I'll be happy to answer any questions you may have about our study.
Great. Thanks, Amir, for going through this recent paper. So if there are questions from the online attendees, please send a chat message. Some people have also been using the Q&A feature. That's fine as well. Any questions here in the room? Amir, I was wondering whether, I know these are really new results, but whether you've socialized this at all with decision-making communities, engineering communities, just because the implications of these different thresholds are significant for investments in infrastructure.
Yes, you're talking to decision makers and infrastructure managers. We've started with energy infrastructure. We were talking to natural gas, SoCal Natural Gas, and they have a lot of facilities in coastal areas, and we are doing this type of analysis for them, updating their risk for different type of infrastructure they have. We have a project funded by the state of California to look at some critical locations, but we are planning to do that more talk to more and different types of sectors and get more feedback.
Okay, great. Thanks, Amir. I haven't seen any other questions come in via the chat box or via the Q&A section, but if anything else comes up, I'll come back to you and ask. So thanks for the interesting presentation.
Sure.
Okay, next speaker and final speaker is Yulong Shah. Yulong, are you on the line? Okay, Yulong, are you there?
Yeah, I'm here.
Okay, great. Yulong, I just transferred control over to your computer, so if you can click the Quick Start tab, and then great.
Oh, I needed to. Oh, I need to share my second screen. Yeah. Can you give me? Okay.
So if you just bring the file up on your screen, then we'll be able to.
Yeah, I need to go green. This is share. Stop sharing. And you give me, and then I needed to share my second. Okay.
Yeah, do you have your slide set? Oh, great.
Yeah,
okay.
I have. And then I can slide it. So, okay.
Great. Okay, go ahead.
Yeah, I'm Yulong Xia from the NCF-EMC. I'm mainly work for the Irma project. And as Dan told you, and I'm working for Irma. The main purpose is for the drought monitor. But now we look at the Irma monitor to look at the opposite case for the Hurricane Harvey and Irma on flooding effect. Okay. And if you look at the bottom, this shows the street view in Texas. Houston, you can look at this is before Harvey and after Harvey. After Harvey, you look at almost everywhere is flooding. Okay. And here, this slide gives you a briefing about Hurricane Harvey. You can look at this is a picture from the Dan's email. You can look at is larger, and this table show you some place like John shows. This is shows about 64 inches. Okay, this is for 5 days period. This is very high. The maximum rainfall for 4 days period, some places larger, 1,000 millimeter. It's about a meter. This is the wettest tropical hurricane, brought heavy rain and caused catastrophic flooding. This shows this caused 83 people died and caused $70 billion damage. Okay. And here show you the initial condition for the soil moisture condition before Harvey landing. You can look at this is I show the top shows the top 1 meter soil moisture normally for 3 days, and the bottom shows the total column soil moisture normally. You can look for this slide. This is the region, East Texas and Louisiana region. It's basically from, if you look at initial condition for soil moisture is wet. Okay, and this is a wet situation, and also if you look at our stream flow normally shows largely positive. This means if heavy precipitation occurs, flooding will be expected. Okay. And this slide shows a movie about the daily anomaly for precipitation, soil moisture, and the runoff and the stream flow. You can look when Harvey come and then brought the heavy rain, and then they bring the soil is saturated, and then produce the total runoff through the river channel, go to the stream flow. this basically, the iron dust look is generally capture the hydrology process from the rainfall eventually go to the stream flow, and because extremely heavy rainfall and relative wet soil cause catastrophic flooding in this region. Okay. And this slide shows you the post-Harvey the impact. And the top shows the soil moisture percentile, and the bottom shows stream flow percentile dailies. You can look when Harvey, after Harvey, and the soil wetness will continue 1 to 2 weeks. You know, this is recover to normal. And if you look at the stream flow anomaly, you can look large stream flow percentile will continue about 7 days, and then from the stream wet to the wet case. And this slide shows you about experimental real iron dust forcing generation. Because our current operation iron dust mainly work for the drought case, I know even they have the moderate effect for the drought monitoring, but still is not shows very important. But if you look at the flooding case, the real time is very important. We use CTC gauge precipitation, stage 2 precipitation, and even name V4 forecast precipitation, as well as the name V4 analysis and forecast data include the radiation at central, and we extend now CDAS data to achieve real-time iron dust system. This shows that we use different sources how to achieve real-time iron dust. And here shows the operation iron dust and the experimental real-time iron dust. Top you can look at the operation iron dust, and the bottom you can look at the real-time iron dust, the daily stream flow anomaly. You can look if we use real-time exact replay in the August 27th, we can find the flooding case. Okay, but if we use the operation iron dust, because we have 4 days behind, even we need to capture 4 days and then get the flooding case. Okay, this shows timing has a large impact for the monitoring flood situation. And now we go to the Hurricane Irma. Irma is another story. We have stronger wind and less heavy rainfall when compared with the Harvey. Okay, because Harvey take the long duration and then with very heavy rain. And also Harvey, the Irma caused about 101 total people died, and also caused about $62 billion US damage. These are both the major hurricane. Okay. And if we look at the soil moisture condition on 9th September, you can look at top shows the top panel shows the top 1 meter soil moisture anomaly, and the bottom shows the total column soil moisture anomaly. Okay, left just shows daily, and right shows past week average. You can look in the Florida and Georgia and South Carolina. Basically, this situation is dry. Okay, if you look at the soil moisture, look is dry, even from top to bottom. Okay. And this shows a movie about the daily precipitation anomaly and the total column soil moisture percentile and the daily runoff anomaly and the stream flow anomaly. You can look at this is when the Irma landing, this is increase the soil moisture, and then generate a total runoff, and eventually river channel generate the stream flow. Okay, and due to the relative less precipitation and also dry soil, this is Irma causing less severe inland flooding in Florida, Georgia, and South Carolina when compared with the Texas Louisiana case. But because our model didn't include the storm surge process, this is only consider the precipitation cause flooding, not include the storm surge part. Okay. And this shows a different soil and hydrology process impact for soil moisture and stream flow. You can look at this shows top 1 soil moisture percentile. This shows multimodal mean case, and this shows NOAA, mosaic, and weak. If during the Irma, you can look at all the is very wet, extremely wet case. Okay, but after 9 days, this shows quite different. Okay, if you look at the NOAA, almost become the normal or dry case. But if you look at the weak model, it shows still is very wet, and the mosaic in between. If you look at the multi-ensemble mean, shows the relative wet. This means the different physical process will affect your stream flow calculation, soil moisture calculation. After the Irma, they through the how many days they just become normal and recovery. This is still a challenge for the community. Here I just raised a question. We use a different even field capacity, the root zone depth, and the evaporation algorithm and the parameterization, and the central is the effect our result. Okay. And here shows your operational and the real-time iron dust. Okay, for Irma. This shows the operational precipitation and the stream flow anomaly, and this show you the real-time precipitation and anomaly. You can look at either if we use the operational, we have the 4 days behind, and then we cannot capture flooding case in time. Okay, but if we use the experimental model, because we use name V4 12-hour forecast, this shows some inaccuracy if you compare the observation. Okay, but even so, I think the timing may be more important for real-time monitor in the future. Okay. And this slide shows your iron dust and unsafe geodust development and future plan. We just released our white paper. The white paper shows you about vision, requirement, and implementation. And you can download from this is the iron dust website. And they basically give the iron dust how to develop from different steps, and also unsafe geodust. Eventually, we wanted to unify 2 systems into the unsafe unified iron dust system. This is give some the outline. You can check this is a white paper and see we how to develop our iron dust system. The iron dust development and update will help enhance our iron dust capability for both drought and flooding monitoring task. And here I give a summary. The iron dust can monitor many features of flooding caused by hurricanes Harvey and Irma, but going to fine and grade scale, then the current ANDAS could provide additional details like national water model, go to the 1 kilometer. Okay. Harvey brought heavy precipitation over long duration over soils in Texas and Louisiana were relatively wet before landfall. These conditions caused catastrophic inland flooding. And Irma had a strong wind over the large land area and less precipitation we compare to the Harvey. And affect state of Florida, Georgia, and South Carolina have relatively dry soil before landfall, potential mitigating the level of inland flooding observed. And the real-time ANDAS does definitely help monitoring flooding situation when compared with the current operational with a 4-day delay. And the ANDAS development and upgrade include addition of data simulation, model physics, and parameter upgrade, and increase the file resolution will further enhance its capability to operation monitor drought and flooding, occurrence, duration, and termination. For details, you can see the recently released white paper. On the last slide, I show you the experimental real ANDAS product. You can download it from this website for internal look. And also I show you experimental real-time ANDAS drought monitoring. And also I gave some link in the ANDAS website and the ANDAS publications. And here shows the movie about the stream flow anomaly for both the hurricanes Harvey and Irma. I stop here, and now I can take any questions from you. Thanks.
Great, thanks a lot, Yulong. That was a really interesting overview of what NLDAS shows for the event. Let's see, there was a question. Okay, I think it's actually more logistical about WebEx. Is there a question there? Yeah, Anna Rita.
Hi, Yulong. I have a question. I think you commented that the current NLDAS does not account for coastal flooding. I'm wondering whether under the topic of NLDAS development, I think the last bullet on your previous last slide, whether there is a way to account on that as part of future development, for example, as part of data simulation or something else?
Yeah, I think the data simulation CRISPR group and our group will, if you look at our white paper, we plan for the after real-time upgrade, we will go to ANDAS 3. And for the coastline and the storm search part, we just wait the community and the research community. If they have the development model and the sub-model can easily to incorporate the ANDAS, we are happy to transition to operational.
Okay, thanks, Yulong. I don't see any other questions online. Anything else in the room here? So there was one question for John that we didn't have time to get to. John, are you still on the line?
Yep, I'm still here.
Okay, great. So there was a question, the person was wondering whether Hurricane Harvey shares any similarities with Tropical Storm Allison, which also produced a significant amount of rainfall over the Houston area.
Yes, both storms basically stalled once they made landfall. Allison was not the continuous rainfall producer. It was more of a localized flooding event in part of Houston rather than being the widespread multi-county sort of event that Harvey was. And also Allison occurred in June, so it didn't have as warm sea surface temperatures to feed off of and load water into the atmosphere that Harvey was able to work with.
Okay, great. Thanks, John. So that's it in terms of questions on the line, and I think we'll adjourn at this point. I want to thank the speakers. I know this was a somewhat long webinar, and I appreciate you all hanging on the line. I thought the talks were really interesting, covered a lot of ground over the last couple hours. For the attendees, I know some folks tried joining earlier. We're having difficulties because we were over capacity for a lot of the webinar. We're going to have the recording and all of the slide sets available on the website probably in the next couple of days, so check back if you want to see other talks or go back and see something that you were on the line for. And I want to put a plug in for the webinar tomorrow, which is going to be focused on prediction across timescales, and Heather Archambault is going to host it. And while I have the platform, I just want to say Heather's moving up to GFDL next week. She's leaving Climate Program Office, and I just want to say that it's been really enjoyable to co-host the webinar series with you for the last few years, so thank you for everything you've done, and you get to do one more tomorrow, which is great. Yeah, please check out our website, some of the past webinars, sign up for the email list so you can hear about future webinars. And that's it for me. Again, thanks so much to the speakers for taking the time to present. Each of the talks was really very interesting, and we really appreciate you sharing some of your research with us. Thanks, everybody. Take care. Talk to you tomorrow.
Okay, thank you. Bye.